Hi everybody, this recording is for Engineering 111 lecture number 2. As a reminder, we had to have a recorded class because I'm going down to Clemson, South Carolina today to work on the fundamentals of engineering exam. So we're going to be talking about engineering units and prefixes today. Brief discussion about orders of magnitude and how those can be used for estimates of solutions before you actually do the full-fledged solution. We'll talk about significant figures and units. So before we do that though, let's take a look at a couple of reminders. Please remember that your introductory assignment that I handed out last time should be uploaded to MU Online before 12 p.m., that's noon, tomorrow, Friday, January 13th. If you don't have the paper that I handed out in class, then that's also available online, so you can find the assignment and the questions that you need to respond to. The other piece of paper that I gave you along the lines of homework in class last time was homework 1. And you still have plenty of time to solve that. It's due on Thursday the 19th of January. So you'll be submitting that in class on paper. That won't be an electronic submission with that assignment. And we'll have some time in class on Tuesday to also address any questions you might have for that assignment. Okay, so first off we're going to look at engineering prefixes, and there are a lot of these that probably are very familiar to you in the context of computers. For example, when we talk about kilobytes, megabytes, and now even terabytes. Some of these are probably not as familiar. When you go above terabytes, the peta, exa, zeta, iota, those are pretty uncommonly used. And so you understanding what the prefixes mean, your responsibility is going to extend from tera down to pico. And so here under the symbol you can see the appropriate symbol that goes with each one of those prefixes, and then the conventional notation is how many, this is a base 10 measurement system. And exponential notation is another way of expressing that. And in most cases we find that students have been well acquainted with these concepts in high school years, but you're going to be using them a lot more frequently now than you might have before, because engineering calculations sometimes have very big quantities. For example, when we talk about volumes of earthwork that have to be excavated for the foundation of a building. So this next slide just sort of zooms in on the upper scale of the range of prefixes, and the ones that I use most often in environmental engineering when I'm teaching are mega and kilo. Some of these are a lot more rare. It's not common to use deca or hecto, but still it's important to be acquainted with these and be prepared to use them and interpret them in the problems when they come up. Here's a zoomed in look at the lower scale prefixes in the SI system. So here's what I would recommend. Since you're responsible for knowing the range tera through pico, you should make some flashcards and memorize these if you don't already know it. Everybody learns a little bit differently, but you should be able to know the conventional notation and the exponential notation for each one of these terms, tera through pico. Each one of those represents an order of magnitude, meaning that they are 10 times greater than the one before it. And sometimes when we talk about an order of magnitude estimate, we're discussing something that's just roughly accurate to about a factor of 10. So if we talk about this factor of 10, 10 is an order of magnitude greater than 1, because it's 10 times greater than 1. And if we look at 1,000, 1,000 is an order of magnitude greater than 100. And so if you're going to do an order of magnitude estimate of the tuition at Marshall, for example, on an annual basis, then you'd say it's between $1,000 and $10,000. And so that range is an order of magnitude. I think you get the idea about an order of magnitude. Now, you can do this estimate by rounding everything to the nearest power of 10. That can be all of the input variables for whatever is being multiplied together, for example, or sometimes maybe you'll just round off the final solution to the nearest power of 10. When you multiply in exponential format, of course, you simply add the exponents and divide by subtracting exponents. Now, there's an example I'd like to show you of order of magnitude estimates, and that is a coal-fired electric generating plant. So let's say that it consumes 600 tons of coal per hour, and if it's operated continuously, meaning round the clock, 24 hours a day, 7 days a week, 52 weeks per year, then how many tons would the unit consume? So of course, what we said is we round everything off to the nearest 10, base 10. So this would be 1,000 tons of coal per hour. Now, the question now becomes, how many hours are there in a year? And so what you can do is you can take the 24 hours a day, 7 days a week, and find out the number of hours per day. If we say that there are 600 tons is closest to 1,000 tons per hour, 24 hours per day, the closest order of magnitude, it's not going to go up to 100 hours per day, it would be 10 hours per day. And 365 days per year would go to 100 days per year. And so you can see that these are really rough approximations, but we are only interested in the answer to the nearest order of magnitude. And here is the exact answer where we do the calculations on a precise basis. And you see when you do that, it's about 5 times 10 to the 6th tons per year. But what about our sloppy estimate where we are rounding everything as much as to the nearest order of magnitude? Well, we got pretty close. This was saying 1 million tons, whereas this was 5 million tons, but that puts us in the same order of magnitude. So you can see the value if you don't have a calculator handy or you just want to do the calculations as quick as possible to a magnitude of estimate, an order of magnitude estimate type calculation. We could improve on that though, right? We don't necessarily have to round 600 tons per hour to 1,000 tons per hour. We could, instead of rounding everything to an order of magnitude, we could order it to the nearest significant figure. And so we would leave the 600 tons per hour as 600 tons per hour, and we'd round 24 to just 20, eliminating that second digit. And likewise with 365 days per year, it's a lot more accurate for us to say that there's about 400 days per year. I should say days per year. All right. So if we do that calculation, then that gives us 4.8 million tons per year. And if you remember, our exact estimate was 5.2. And so now, by improving the accuracy by one significant figure, that really gets us a lot closer to the correct answer that we already know about. Now, the concept of significant figures is really important, and we find that sometimes students either don't include enough significant figures or include too many significant figures as they do their calculation. And what it is really meant to represent is the accuracy or the dependability of the data that's being used. So if we take this example as an illustration, how accurately are they measuring the mass of coal per hour? Is it exactly 600.00 tons per hour? Or when we got that information from the coal plant, was that maybe rounded off to the nearest 100 tons per hour? So we don't want to imply a greater degree of accuracy than we actually have. On the other hand, 365 days per year, that's pretty accurate. We know that to a level of precision, so we could have justified leaving 365, and so that in that case there'd be 3 significant digits that we are including in our calculations. So the calculator doesn't always know the precision of the data that's going into it. And so it'll calculate as many decimal places as it can in its memory, but it's possible that all of those decimal places aren't actually lining up with the precision of the underlying data that we used. So it can give you unreliable answers. Now, zeros, if they're written on the paper, are going to, these trailing zeros are going to imply a precision that you may not actually want to be claiming. So these trailing zeros are considered significant. The leading zeros are not considered significant figures. Excuse me. Now in exponential notation, this same number expressed as an exponential notation, you can see that when we are in scientific notation, all these extra zeros are implying that you're able to measure the thing to that much accuracy. So here there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 significant figures. So looking at this further, each of these number groups have 3 significant figures. 175, 25.5, 1.85. In each case, 0.00125, there are 3 significant figures. These extra zeros don't count because they have to be there in order for us to accurately represent the 125, but then they don't actually contribute to any additional significant figures. Now, in the case of 1100, it isn't clear when we represent it just in this standard notation. In exponential notation, it's a lot more clear because we can have zeros after the 0.011, and then it would be clear if there's 2 significant figures in that case. But if we wanted there to be 4 significant figures, for example, then we would just put a decimal after that. And that decimal would mean that we have these zeros to a level of precision that's different than if the decimal isn't there. All right. I know that a lot of this is things that you've seen before, and so just consider it as a brief review, the rules of rounding. When you're rounding to the nearest tenths, then you're going to round down if it's 0 through 4, round up if it's 6 through 9, and then in the case of if the hundredths digit is 5, then you have to look at the tenths digit. And so if it's odd, you round up. If it's even, you round down. And this last thing might be a little bit new to you. You might have in the past been in the habit of always rounding up for 5. But the reason why this rule is sometimes suggested is that you don't want to have your data be lopsided. You know, if you were rounding a lot of different things, if you always were rounding up, then your answer at the end would be artificially too high. So by alternating back and forth between rounding up and rounding down, in the case of if it's even or if it's odd, then that prevents you having a bias that's always going in the same direction. So here you can see 33.75, the 7 is odd, and so we rounded this up to 0.8. But in the case of it being an even digit, this 6 is even, and so 0.65 we rounded down to 0.6. And again, the reason for that is so that you're not always rounding up and creating a skew in the data. All right, so let's take a look at what to do when we're adding and subtracting. If you have 164.57 and you add 4.3 in your calculator, then your calculator is going to assume that when you type in 4.3 that it is exactly 4.3. And so your calculator thinks really in its mind 4.30000. But what we know is that the last digit of accuracy that we had was to the tenths place here, because 4.3, it was just to the tenths that we were measuring that. And so when we write down our final answer and box the solution on the paper, we would take that calculator answer and we'd round it to the nearest tenth, since we were to the nearest tenth in one component of our data. And now the same thing is true in this illustration, where if we only knew it to the nearest digit, 4, then we don't know if it's 4.0 or 4.00, so we have to round our final answer to the nearest whole number. And so instead of 109.259, which is what it would say on the calculator, you round that to 109. Multiplying and dividing, things get a little bit more tricky. And so let's take a look at the illustration of 25.34 multiplied by 7.3. The calculator is going to have even more digits than it did before. You know, each of these, this was to the nearest tenth, this was to the nearest hundredth, and we had 4 significant figures for the first number and only 2. Because there were only 2 significant figures in one of our number groups that we're multiplying with, and that means in the end we should round off to the nearest 2 significant figures. So 184.982, we'd round that off to 1.8 times 10 to the second. And so 10 to the second, you'd move the decimal place 1, 2 places, and so that's how you know it's 10 to the second. And so it's 1.8 times 10 to the second because we had to move the decimal place over twice. The same kind of operation exists when you're dividing, where your limiting factor in this calculation is going to be that one of your numbers had 3 significant figures, the other had 4. So we have to go with the lower of the 2 when reporting the final answer. There would be 3 significant figures in the end. All right, now units are really important. Sometimes we get in the habit for just trying to speed things up or saving space on the paper to just write the numbers, but without the units that go with them that help us to make sense of what they are. 123 may be a distance in feet, 3,500 may be pounds per square foot, 43,560 is the number of square feet in an acre. And so these numbers make a lot more sense and they have more meaning when we also include the units along as we do the calculations. So units are really important, and if you write the number but not the units along with it, then you may have a deduction in points. It's not completely correct. And another thing that's helpful is that sometimes you can avoid mistakes by including the units. It might be that you catch a discontinuity if you're trying to multiply things together that have units that don't quite match up. So you'd be able to catch your mistake and reconsider the equation that was used. Now here's a structural engineering example that you'll come back to in the future when you're doing some structural analysis in the junior year. Let's say that we have a beam that is being loaded at the midspan and it's supported at each end. And so it's going to deflect in response to that load. And if we wanted to find out what's the deflection, if we wanted to measure how much that is, you can see the formula for measuring the maximum deflection depends on the load that's applied, the beam length, and each one of these variables has units associated with it. And we can put the units into the formula, and then that would tell us what the units that come out of the formula should be in. So deflection in this instance should be measured in inches, because if the load was in pounds and the beam length is going to be in inches and it's cubed in the formula, then that gives us inches cubed. And then the moment of inertia is going to be inches to the fourth, whereas the elastic modulus PSI is pounds per square inch. And so then that simplifies to pounds times inches squared. And then the pounds cancel. 3 divided by 2 gives us just the inches as a leftover unit. So even if the deflection units weren't defined for you, you could put the units of each of the individual variables into the formula and derive those units. Here's another illustration in the area of pipe flow, where you're calculating how much energy is in water as water flows through a conduit. And so the units of pressure, as shown here, are newtons per meter squared. That's how we measure pressure. And unit weight is newtons per meter cubed. Velocity of flow, meters per second. Gravity is measured in meters per second squared, and elevation is in meters. Now look that each of these three terms are being added together. And for us to add them together, then that means that all three of those terms have to have the same units. The easiest of these three terms to know the units for immediately is elevation, because it's just meters. But what that says is that we have to have meters for each of the other two terms as well. So let's see if that's true. We had newtons per meter squared divided by newtons per meter cubed. And so the newtons cancel. This meters cubed goes from the denominator of the denominator, so that flips it up into the numerator, and we end up just with meters from that. And the same thing is true when we look at the velocity head term. Velocity is meters per second, and so if it's squared, then it's meters squared per second squared divided by g, and all that's left when the seconds cancel and this meter takes 1 out of the exponent is meters. So this equation is dimensionally homogeneous, meaning that we can add the terms together since they're all in the same units. Appropriateness of units is also an important factor to keep in mind. This illustration is that 18 years is the same as 0.18 centuries, which is the same as 218 months, and so on. But usually when people ask us how old we are, we would report our age in years rather than any of these other terms. It's also the case when we're working in engineering calculations. In the case of civil engineering, like construction, we talk about thousands of pounds, and a KIP is 1,000 pounds. And that's because the strength of concrete and the strength of other materials that's used in construction is most appropriately described in terms of thousands of pounds. In the SI unit system, there are newtons, meters, kilograms, and so on. And electrical engineers have to work in units of ohms, amps, volts, and so on. We're going to work problems through the semester that will acquaint you with each of those units. And sometimes you have to convert from one to another, 12 months in a year, for example. And professors love to do the thing where they will mix up the units that are given in the problem statement to force you to convert it, so that you'd have to maybe take a given duration in months and convert it into years before you do the calculation. Alright, so that's all I wanted to share with you today. Before we wrap up, let's take one last look at these announcements and remind you that the introductory assignment is due by Friday at noon, and then homework 1 is due on Thursday the 19th. And we'll have some class time on Tuesday to spend on that, but you're welcome to get an early start so that you can bring any questions you might have to class. Hope you have a great day, and I'll see you next Tuesday.